So let's understand inverse functions using a simple idea. So how functions map inputs to outputs and how we can reverse that mapping. So let's imagine this. So let's say this is my domain and here's my range. And in the domain, let's say I have an element x. Okay, so we have a function f that takes this input x and gives output as f of x. So this happens with function f. So we can say x maps into f of x using the function f. Now suppose that we want to go back. We start from f of x and we need to get back our x. So we need a new function that undoes what f did. So the function, we can take that function as g. So what g does is, g takes f of x and gives the output x. On the other hand, f does is, it takes input as x and it gives the output as f of x. So let's name this function as g. Okay, so this function g is very special and we call this g as the inverse of f, because what g does is, g actually undoes what f did. G is the inverse of f. And we use the notation f superscript -1. So we use this notation to represent inverse. So in other words, f inverse takes the output of f and brings us back the original input. Okay, so this is the idea behind inverse function. Okay, so this is the formal definition of inverse function. So let's say we have two functions, f and g, and we say the function g is the inverse of function f if the composition of the two functions f and g is equals to x. So as you know, there are two possible compositions for f and g. They are f of g of x or g of f of x. So if both these two compositions is equals to x, we say g is the inverse of f, and we usually write this as g equals f inverse, and we read this notation as f inverse. So again, this means that the functions g and f actually undo each other. So we can write it like this. So the composition of f inverse is equals to x, or f inverse of f of x is equals to x. So in plain terms, if you apply inverse functions first and then the original function, then you get back where you started. And also if you apply the original function first and then inverse, again you return the original input. So this is the idea of inverse, and they reverse each other's effects. Okay, so remember, in order to show that two functions are inverse of each other, what you have to do is you have to take the compositions of the two functions and you have to show that it is equals to x. If it is not equals to x, the two functions are not inverse of each other. So let's try some examples now. So let's start from here. So in this example, you have a function f of x, and you have to test which function is the inverse of this f of x. And here we have two candidates. To do that, we need to get the compositions. So if the compositions of the two functions is equals to x, then we can determine they are inverse of f of x. So let's first of all, let's start with g of x. So we have to get the compositions. There are two possible compositions. First of all, let's start with f of g of x. If it is equals to x, then we have to check the other way around as well. So let's start with the first one. So let me take the composition f and g. First of all, I'm going to replace my g, which is x negative 4 over 3. And then I'm going to simplify my f. I'm going to use the definition of f. So f of x is equals to this. So now instead of x, I have this function. What I'm going to do is I'm going to take this, the definition of x, and I'm going to replace this x by this expression. So it's going to be 3 over, instead of x, I'm going to write x minus 4 over 3 minus 4. So in the denominator, I have here a fraction and a constant. So in order to combine these two terms, I need to rewrite this as a fraction. To do that, I'm going to multiply both top and bottom by 3. In that case, you'll get 3 over x minus 4 over 3 minus 12 over 3. So now you see in the denominator, you have two fractions and they have the common denominator. So now you can combine these two expressions. If you combine them together, you'll get x negative 4, negative 12 over 3. Okay, so now it's just this 3, you can write this as 3 over 1. It's the same thing. So it seems like a fraction you have to divide by another fraction, which means what you have to do is you have to multiply this term by the reciprocal of the denominator. So it's gonna be 3 multiplied the reciprocal of the denominator, which is 3 over x minus, if you combine these two numbers, it's negative 16. So this is going to give you 9 over x minus 16. So you cannot simplify this further. So this is not equals to x. So this is not equals to x, which means so g of x is not the inverse of f of x. It's because if you take the composition, it's not equals to x. So now we have to move into the next candidate, and you have to follow the same procedure to see whether it's the inverse of f of x. Okay, so now let's again take the composition. Let's start with f of h of x. So f h of x is 3 over x plus 4, that is my h of x. So now I'm going to take the definition of f of x, and instead of x, I'm going to use this expression. So it's 3 over, instead of x, I'm going to write 3 over x plus 4, and I have a minus 4. So it seems like these two terms get cancelled. So then you will have 3 over 3 over x. So now again is just to simplify this, you have to multiply the top by the reciprocal of the denominator. So it's going to be 3 multiplied by the reciprocal of denominator. It's x over 3. So the reciprocal of the denominator means it just you have to switch the top and bottom. So now you see these 3's will cancel out, and then it will simplifies into x. Okay, it seems like h is the inverse of f of x, because here I have taken the composition and the composition simplified into x. But still we are not done with the problem. You have to check the other way around as well. So you have to check the composition of h and f. So let's try to simplify this and see whether this is also equals to x. If so, we can conclude that the h is the inverse of f of x. Okay, so here I'm going to replace my f of x, which is 3 over x negative 4. And then I'm going to use the definition of h of x to get this. So here if you have x, you can write 3 over x plus 4. So now instead of x, I need to replace this expression. So just 3 over 3x negative 4 plus 4. Again, here you have a constant divided by a fraction. So what you can do here also, you can multiply the top by the reciprocal of the denominator. So it's x negative 4. You have to use the parentheses plus 4. So this 3 and this 3 will cancel out. So you will have x negative 4 plus 4. So the plus 4 and the negative 4 will cancel out. So you have x. So here you can clearly see, if you take the compositions of f and h, the both compositions, that gives back x. So that means h is the inverse of f of x. So what you can do is, you can write f inverse of x is the h function. You can write this. So this is the inverse of f of x. Okay. This is the second example. Again, you have a function f of x and you have to check which of this function is the inverse of f of x. Again, you have two possible candidates. Let's start with g of x. Let's take some compositions. First of all, let's start with f of g of x and see whether this is the composition. So first of all, I'm going to replace my g of x, which is 2x plus 5. And then I'm going to use the definition of f. So here f of x is this. So instead of x, I'm going to replace this expression. That is 2x plus 5 minus 5 over 2. So in the top, these two terms will cancel out. And then you'll get 2x divided by 2. So here the 2's will cancel out and you'll have a x. Okay, this is a good sign. It seems like this is the inverse, but still we are not done. You have to check the other way around as well. So you have to check the composition of g and f. So here let's replace g f function, that is x negative 5 over 2. Okay, so now let's use the definition of g, which is 2 multiplied by x. So instead of x, I need to write my input in this function, which is x negative 5 over 2 plus 5. Okay, so here the 2's will cancel out and you have here x minus 5 plus 5. So the 5's will go away, which you have x. Okay, this is really good. So both the compositions gives back x. So that means g is the inverse of f of x. So you can write here the inverse function of f is equals to g function, which is equals to 2x plus 5. So it seems like this is the answer, but we have another function to test. So let's quickly test whether this is inverse or not. So here also I'm going to take the composition f, the composition of f and h. So let's replace h function. So x negative 5. So f of x is x. Instead of x, you have to write the expression, that is 7x negative 5 plus 5 over 2. Okay, again in this scenario, you have a fraction in the denominator and this is a constant. So you have to have a common denominator. To get the common denominator, I'm going to multiply here the both top and bottom by x negative 5. So this doesn't affect my problem because these two terms will cancel out. So here you can write, since you have a common denominator in the top, you can combine the terms. So it's going to be 7 plus 5x minus 5. And in the bottom, you have a 2. So let's remove the parentheses in the numerator. So it's going to be 5x minus 25 over x negative 5, and you have a 2 in the bottom. So it's 5x minus 18 over x negative 5 over 2. Okay, so if you simplify this, you will not get x. If you want, you can try to simplify this expression and check, but it doesn't simplify into x, which means h of x is not the inverse of f of x. So the inverse of f is g. We already proved that over here. So in order to verify whether two functions are inverse or not, what you have to do is you have to take the compositions. You have to check the both possible compositions, and if both compositions gives you back x, which means they are the inverse of each other.